Thank you. My name is Dr. Abhishek Kumar Ghosh. I am an assistant professor of mechatronics engineering at the University of Dhaka, Bangladesh. And welcome to my talk, where I'll be mainly discussing our research on developing a wearable fetal movement monitor. Specifically, this study deals with a comparative analysis of different kinds of sensors that we generally find in literature for detecting fetal movements. My co-authors are Omar-Ibne Shahid from the University of Dhaka, Dr. Nowlan from University College Dublin, and Dr. Ravi Vaidyanathan from Imperial College London. So this is the content for my presentation today. I'll start with the motivation for this work and then define the objectives. After that, I'll briefly discuss the materials and methods used in this work. Then we'll discuss some of the key findings, and then I'll draw some major conclusions from this work. And finally, I'll end my talk with a glimpse of some of the recent work that we are doing to translate the technology that we developed during this work. Okay. So why do we need to monitor fetal movements? That is the first question that comes in our mind when we hear about this research. And the reason is that numerous studies have shown that fetal movements can work as a biomarker for fetal health. And it has been associated with a number of fetal health issues, including fetal distress, growth restriction, hypoxia, placental dysfunction, etc. And on top of that, several studies have shown the potential of fetal movements to work as a biomarker to kind of give us an understanding of the impending risk of stillbirth, which is a significant problem for prenatal healthcare globally. 2020 United Nations studies have shown that around 2 million stillbirths are still happening every year, which is a very significant number. And the rate at which the number is going down is not very good, slowing down every year. And so you can understand the significance of the problem, but at the same time, the failure of the current technology that we have to predict the risk of stillbirth. So that's why we're trying to develop something new based on the other biomarkers of stillbirth risk prediction. The second question is, why do we need a body-worn FM monitor? It's because the current technology, which is mainly based on ultrasonography, is not good enough for providing us a regular continuous monitoring in a home environment. So a wearable device will provide that facility. And then this study particularly deals with the comparison of different sensors for designing the wearable FM monitor. And that's because the in literature, different people have used different types of sensors, and the methods are different, the definitions are different. You can't really compare between them based on the findings from the study. So we wanted to compare between them to find out what's the best sensor, and if we get any benefit when we combine multiple different sensors in terms of improving the detection accuracy. So these are the objectives. So in this study, we wanted to design a wearable FM monitor, combining different types of the most prevalent sensors that we got from our literature review, and then to develop an algorithm, collect data, analyze it, and see how different sensors perform in terms of both performance and their response characteristics. And finally, to try to find the optimum sensor combination for designing a reliable wearable fetal monitor. So here you can see the hardware systems that we used for this study. So it's a custom-made wearable device. So we found that in the literature, 3 types of sensors were most prevalent: accelerometers, acoustic sensors, and piezoelectric sensors. So by the way, these are kind of vibration detectors that detects vibration of the maternal abdomen when a fetus moves. So we used one of each of these sensors on either side of the abdomen. And we also added an additional accelerometer on the back of the device that basically detects the movement of the mother, because that creates a lot of noise that we need to get rid of. And this is the data acquisition system that we made. So it samples the data at 1024 hertz and with a 12-bit resolution, with and then stores it on an onboard micro SD card that we later on extract and process on our computer. For this study, we collected 33 hours of data from 5 pregnant participants with this device. So during the data collection, mothers are also pressing a button to identify their senses of fetal movement. So those were the ground truths for this work. And we wanted to replicate the actual environment of the use. So we sent the device to the user's home, and the data collection was, totally managed by the participants themselves. But one instruction was that to refrain from other activities while data collection, because the participant has to sense the movements and create those ground truth levels by themselves. So that's why that was a condition that was imposed. And then this is the algorithmic architecture that we have developed to analyze the data. So we started with the raw sensor data from all the sensors, then pre-process them, just bandpass filtering so that we get rid of the high and low frequency noises. Then we segmented the data to find out the locations where the fetal movements, the highest possibility of getting fetal movements. So the segmentation process was a data-dependent process, slightly dynamic process. And then we fused the segments from different sensors, as well as with the segments from the maternal body movement detection maps, the body movement detection sensor, to get rid of the body movement noises. After that, we extracted features from each segments, from each sensors. Then we use those features to train and test machine learning classifiers. We tried different ones. Eventually, we settled down with neural network, which was performing better than others. And then we compared that with the maternal sensation again to get the performance of the device. The performances, we express the performance in terms of different metrics, like sensitivity, precision, F-score, and AUC of PRC curves, etc. So now let's look at the results of our study. Here you can see responses from different sensors to fetal movements. So the red dots that you can see here are the markers from the mothers, and the other ones you can see the responses of the sensors. On the top panel, you see the response from the IEEE accelerometer, which was detecting maternal body movement. And that accelerometer was on the back side, so outside of the front abdominal region, so that we, so that we can isolate that from any kind of fetal movements. And then at the bottom, you can see the results from the algorithms and all that. So if we zoom into one of the detections, this is what we see. So as you can see, the response looks slightly different, especially for piezoelectric diaphragm that we use. They were quite similar in case of accelerometer and acoustic sensor. And we can see different kinds of shapes as well in case of the spectrograms. So the shapes, the spike-like shapes were similar for accelerometer and acoustic sensor, but the shape was kind of a bit of triangular in case of piezoelectric sensor. When you look into the power spectral density distribution for all the movements, so these two are for specific one movement. This one is the average distribution of power spectrum for all the detections that we have. And we can see that the distribution was quite similar for accelerometer and acoustic sensors. In all three cases, the power was more concentrated below a frequency of 10 hertz. But in case of piezoelectric sensor, it's totally concentrated. There was hardly anything after 10 hertz. But in case of accelerometer acoustic, we got some energy after that. So that's the difference. And when we look at the detection performances, we see again the very in case of acoustic sensor and accelerometer, the performance are very similar. The F scores. but the piezo was outperforming them significantly. When we did the statistical testing, we saw the difference was statistically significant. When we tried to fuse data from different sensors, we saw the performance was improving gradually. The best performance, obviously, we got when we combined data from all three sensors, which was an F score of 179. But we saw that the performance of the acoustic and piezo was very similar, just 1% less, and the difference was not statistically significant. So we decided this is probably the optimum combination of sensors. And also, when we look into the the performance across different participants, we can see that that red line is showing the performance of the piezo, which was more consistent across the participant as well. And then we also tried to evaluate how the performance relates with the gestational age. We saw it, it was correlated. Performance was going up with the gestational age. We think that with the growth of the fetus, it becomes mature, the movement becomes stronger, easier for the mothers to feel, at the same time easier for the sensors to pick up. So, the performance starts to go up. And based on the study, we draw these conclusions. First of all, we saw that the accelerometer and acoustic sensor, they are performing very similar to each other, and their signal characteristics were also very similar. The piezoelectric sensor, on the other hand, has a different kind of signature and was outperforming both accelerometer and acoustic sensor. And the combination of acoustic and piezo was giving us the optimum combination of the sensor, and the performance improved with the gestational age. So finally, this is a glimpse of our current ongoing work. On the left, what you see was the research that presented in this particular presentation. At the middle, what you see is our current version of the device, which we developed with the funding from Wellcome Live in Utero program. So, and what we envision is on the right side. So this is the future version of the device, where we'll be converting the device into a very easy to wear small sensor patches. And we are extremely grateful to all the participants who kindly cooperated with us and gave their data. We are also thankful to our funders. And finally, this is my team who are working on the project at the moment with the Professor Nowlan from University College Dublin. So she is our PI for this project. So thank you all. That's all.
Okay, thank you very much.